Basic transmission theory. To understand the satellite link design, first of all, we have to understand the basic transmission theory, and then we will impose the complexities associated with the uh, satellite communication system. So first we will consider the flux density and the link equation. Here we are assuming that we have a source which is isotropic in nature with effective isotropic radiated power PT watts. Okay, so we have a receiver right here. Receiver area is a meter square. The distance is r meter. Then the flux density at a distance r for this isotropic source can be written as F equal to Pt by 4 pi r square. Actually, this 4 pi r square is the uh, area of hypothetical sphere around this isotropic source. So if you consider a hypothetical sphere of radius r around this isotropic source, then all the power Pt radiated by this source should pass through that particular sphere, area of that particular sphere, right? So area of the sphere is 4 pi r square. So what should be the power per unit area? So power divided by total power radiated divided by the area will give us the amount of power per unit area, right? Now if we consider an antenna with gain G, which is defined as the ratio of power per unit solid angle radiated in the direction to the average power radiated per unit solid angle, that means G theta can be written as P theta divided by P0 by 4 pi, where P theta is the power radiated per unit solid angle by the antenna and P0 is the total power radiated by the antenna. Let me tell you something related to the solid angle. You know, angle means, conventional angle means arc length divided by radius, right? Arc length divided by radius, theta equal to S by R. Okay, but if instead of arc length, if we consider an area A, then if we divide this area by square of the radius, right, square of the radius, that is A divided by R square, then corresponding uh, entity will be called as solid angle. Okay, so theta angle equal to S by R, arc length divided by radius, and solid angle means area divided by radius square. Okay, the unit of the solid angle is steradian. So G theta is the gain of the antenna at an angle theta. So this theta is measured in the direction of maximum power generally. For a transmitter with output PT watt driving a lossless antenna with gain GT, the flux density in the direction of antenna both sides at a distance r meter can be written in this way: the flux density PT by 4 pi r square multiplied by gain of the antenna. Okay, PT by 4 pi r square is the flux density multiplied by gain of the transmitting antenna. That will give you the flux density when instead of isotropic source, if we use some directive antenna with gain GT. So this is the amount of power flowing per unit area. The product PT into GT, it is called the effective isotropic radiated power or EIRP, and it describes the combination of transmitter power and antenna gain in terms of an equivalent isotropic source with power PT into GT watts radiating uniformly in all directions. Now, if we had an ideal receiver antenna with an aperture area of a meter square, suppose this is the receiver antenna and its area is a meter square and gain is say GR. Okay, mind it, we have already said that amount of power uh, per unit area at the receiver point is PTGT by 4 pi r square, that is equal to F. F is the flux density, right? So what should be the receipt power? Receipt power will be the area multiplied by flux density. So PR equal to F into A watts. Now a practical antenna with a physical aperture area of AR meter square will not deliver the power PR. Some of the energy incident on the aperture is reflected away from the antenna and some is absorbed by lossy components. So this reduction in efficiency is described by using an effective aperture AE. So AE can be written as eta A into AR. So instead of multiplying with the original antenna area, physical area of the antenna, we have to multiply it with the effective area. This effective area is actually the original area multiplied by aperture efficiency. This eta is called the aperture efficiency of the antenna. Okay. The aperture efficiency eta A accounts for all the losses between the incident wavefront and the antenna output port. These include illumination efficiency or aperture taper efficiency of the antenna, which is related to the energy distribution produced by the feed across the aperture, and also other losses due to spillover, blockage, phase errors, diffraction effects, polarization, mismatch losses, etc. For paraboloidal reflector antenna, eta A is typically in the range of 50 to 75%, lower for smaller antenna and higher for larger Cassegrain antennas. Horn antennas can have efficiencies approaching 90%. So the power received by a real antenna with a physical receiving area AR and effective aperture area AE meter square can be written as flux density PTGT by 4 pi r square into AE, right? So PR equal to PTGT AE divided by 4 pi r square watt. Now we have the relationship between the effective area and the gain of the antenna, G equal to 4 pi AE by lambda square. So lambda is the wavelength. So in terms of this lambda and GR, we can rewrite this equation. We can rewrite this equation as PR equal to PTGT GR divided by 4 pi r by lambda whole square watt. So this is actually the link equation. This is what you call the link equation. So this equation enables us to determine the receive power at some receiver point from the transmitted power if we know the wavelength and the range. Okay. The link equation is essential in the calculation of power received by any radio link. The frequency or the wavelength appears in this equation for received power because we have used the receiving antenna gain instead of effective area. The term, denominator term 4 pi r by lambda whole square is called the path loss, written as LP. So it is not a loss in the sense of power being absorbed, right? There is no absorption term. 4 pi r by lambda whole square, there is no absorption term, but it is showing that it is a loss because it is in the denominator, right? So receipt power, the expression for receipt power is EIRP into receiving antenna gain divided by path loss. Now this path, why we are calling this loss? Because it is in the denominator. So if this term increases, the denominator will increase and the receipt power will be reduced. So in that sense, it is a kind of loss, though this loss is not associated with any kind of absorption, right? So it accounts for the way energy spreads out as an electromagnetic wave travels away from the transmitting source in three-dimensional space. So it is basically due to the divergent nature of the divergent nature of the electromagnetic wave. In communication system, decibel quantities are commonly used to simplify equation, particularly for satellite communication. Most of the time we have to use decibel. So this equation can be written in terms of decibel as PR equal to EIRP plus GR, receiving antenna gain, it is in the numerator, so plus GR, and path loss LP, it is in the denominator, so there is a negative sign indicating it is a loss. So EIRP plus GR minus LP decibel dB watt. Here EIRP, all these terms are in decibel. So EIRP can be calculated as 10 log to the base 10 PT into GT. GR, the receiving antenna gain, can be calculated as, original expression was 4 pi A by lambda square. We have to multiply it by 10 and take the logarithm with base 10. Okay. Path loss, it is also, basic equation is 4 pi R by lambda whole square, but to in decibel unit we have to take the logarithm and then multiply it with the 10. So it is basically, since there is a square, so it becomes 20 log to the base 10 4 pi R by lambda dB. So this is the basic equation, basic link equation, this one.